Hey everyone, welcome back, and today let's solve Leetcode problem 3433 titled Count Mentions Per User. So we're given an integer number of users representing the total number of users and an array called events of size n by 3. Now each event at index I can either be of the following two types. The first is a message event, right? It's going to be of the form of a list with a message, a timestamp at that index I, and the mentions string at that index I. Now this event indicates that that is a set of users, that a set of users was mentioned in a message at timestamp at index I. The mentions string at index I can contain one of the following tokens. It can contain an ID number, where number is an integer in the range from 0 to the number of users minus 1, and there can be multiple IDs separated by a single white space and even may contain duplicates, where it can also mention even the offline users. All would simply quite intuitively mention all of the users, and here mentioning all online users. Now, the second essential type of the event is the offline event, right? That would have a kind of format of offline, and then the timestamp at index I, and then the ID at that index. Now, this event would indicate that the user ID at this index had become offline at timestamp at I for 60 time units. Now, there isn't a specific unit, we're just assuming units to be our unit, so just think of it as 60 times, if you will. Now the user will automatically be online again at timestamp at I plus 60. Now we need to return an array mentions, where mentions at index I represents the number of mentions the user with ID I has across all the message events. And all the users are actually initially online, and if a user does go offline or comes back online, then their status would also be changed, and rather their status change would also be processed before handling any message event that occurs at that same timestamp. Now, we also very importantly have to note that a user can be mentioned multiple times in a single message event. There is a restriction of that kind, and each mention should be counted separately, right? We technically do have to count duplicate mentions as well. So looking at the examples here, you guys can kind of read them yourself, just to kind of quickly gloss over them. Notice how we're given these different kind of format inputs. We have the number of users, and then we have our events. One could be a message, one could be offline. Notice that we have two different types. In this case, we have three, and our output would simply be an array, and that array, again, of length 2 of 2, 2, would simply just be, again, like it says, as we see here, all the number of mentions, or rather the number of mentions that the user with ID I has across all the message events, right? Now, let's actually get into the constraints here really quickly. So we see that the number of users and the length of our events are going to be between 100 and 1 respectively. And any index I in events is always going to have a length of 3, kind of just confirming what the problem statement said. Events at any index I at the very first, or technically 0th parameter, will always be one of either message or offline. Again, kind of just confirming what the problem statement said. 1 is going to be, or rather the integer of events at index I index 1 is going to be between 1 and 10 to the 5th power, and the number of the ID mentions in any message event is also between 1 and 100. The ID number itself is going to be between 0 and the number of users minus 1, and it is guaranteed that the user ID referenced in the offline event is online at the time of the event occurs. Right? Really, again, just confirming what the problem statement said here. Nothing surprising. All of these were kind of expected upon reading the problem. Now let's actually get into the key observations to really make to solve this problem. And now, before we even get into the code, I will mention that the code is quite hefty, right? It isn't a straightforward, simple solution, particularly with the syntax that I use for the solution with the usage of lambda and decorators. And so you will definitely need to be a little better in the coding side to be able to solve this problem efficiently and correctly, along with being able to solve it, more intuitively and getting the conceptual part of this down, right? So how are we really going to solve this problem? Well, kind of tying back to the first observation that we really need to make, and that is that events must be processed in chronological order, right? That means when two events share the same timestamp, a message should be processed before an a message should be processed before an offline, so that the order actually does matter, right? Now, this also determines why we sort events by the timestamp and event type, very cleverly, because that allows us to more efficiently manage the different event types, right? It's very important that we process these messages, or rather events, in chronological order, right? Essentially, when two events share the same timestamp, we always have to process a message event before an offline one, right? So how is that going to tie into an overall solution here? Well, effectively, we're first going to sort the events by their timestamp in ascending order and the messages before offline when the timestamps time. Now, we also then iterate over the events in sorted order, and before actually handling each event, we'd simply just pop from the offline queue, really just a array that we're going to create in our solution here. Basically, offline queue is just going to be a minimum heap of offline entries where each would contain the time that the user would return and the online, or rather the time that the user would return online and the user's ID, right? Effectively, the whole reason why we're using a minimum heap here is that really we can just efficiently bring back users back online when their offline window expires. And because minimum heaps, of course, do store the smallest value in their data structure at the top of the list, making it very easy to pop out. Right, so we're going to pop from the offline queue before handling each event, and we're going to basically just pop off any users whose return time is less than or actually equal to the current timestamp, and then mark them online again. Now, once we actually start processing them, if the event is message, if the message content is all, we then increment the all mentions count. If the message content is here, we'd increment answer at that index u by 1 for every u who's currently online. Otherwise, if neither of those are true, we then simply just parse the mention list string like u0, u3, u5, or whatever, and increment those user IDs in our answer list. Now, if the event is offline for this user, we simply just set the online array at this user index to be false, and we simply just push a tuple of length 2 of timestamp plus 60 and that user itself into the offline queue. And once we actually finish all the events, we'd simply add the all mentions count to each user's answer because all the mention count would be for every user. Now, sorting would actually dominate this our runtime complexity, and so it would actually be big O of n log n time. And of course, for the space, that is going to be linear, but I'll get more into how that really works after we finish coding up the solution, which brings us to, well, the actual solution. So before we actually start, technically this isn't really needed in the Leetcode editor specifically, but for best practice, I will actually include the different packages and modules that I'm going to be importing, really just to also better understand how this solution works and the different dependencies that we're really using to solve this problem in the most efficient manner possible. So from data class, I'm going to import data class, right? Basically, we're importing data class so that we can actually define a small immutable record type to store all the offline users, and that really just makes our code cleaner by letting us create simple objects with named fields. Now, once we import data class, we're going to do the same thing but for heap queue. Again, not needed, but good for best practice, right? This is quite literally for our offline queue, for our minimum heap, right? It's going to be the standard Python's binary heap implementation, and we're essentially just using this minimum heap to actually efficiently manage the earliest return times of our offline users. And finally, again, not needed, but from typing, we're going to import list, right? And we're simply just importing a list for the type hints, so the function signatures are more readable, and you guys really understand what the functions are supposed to return. Right, now, before I actually get into the solution class here, I'm going to create a class of my own, and that is going to be for the offline user. This is the whole point of why I actually imported this data class module. So I'm going to first throw in a decorator at the top in the front of the class, and so it's going to be at data class, and I'm going to pass in a parameter of frozen and set that equal to true. Oops. Once I've actually initialized my decorator, now I can actually create my class. So quite intuitively, I'm literally just going to call it offline user. I don't think there's a better way or more intuitive name for this. Sorry, I don't need parentheses. Once I initialize this class, I'm going to have a return timestamp. It's going to be of type int, and I'm also going to have a user ID, which is also, of course, quite intuitively going to be of type int. Now, I'm going to create a underscore dunder method here in this class here. I'm just going to call it LT. I don't really know what else to call it here. And basically, it's just going to be the less than method, right? Now, I'm going to pass in, of course, self. I'm going to pass in other for my parameters here, and simply just return self.return timestamp. And we're going to return a Boolean value of if that's actually less than other.return timestamp. Cool. And we're using LT because that simply just stands for the less than method in Python, right? Really just simpler, right? It makes it a lot easier to really work with. All right. Now, what are we really doing here? How does this class really function, and what's its significance to our overall solution? Well, again, we're essentially just defining a very small offline user data class, and it's going to have two fields, as you can see. or two parameters, if you will. The first parameter or field rather would be the return timestamp. That would simply just be when the user will become online again, and the user ID would be the second field, which is basically just representing which user this actually is that we're processing. And the reason why we have frozen is true is because we're setting this class to be frozen so that it's immutable. And we're also implementing this LT dunder method here. Basically, it's just, again, like we glossed over, it stands for the less than method. So Python's heap can actually compare instances by return timestamp to make a minimum heap by the return time, right? Now that we've had this immutable class initialized, now let's actually get into the class solution, or the solution class here. This is really what is going to kind of form our overarching solution, if you will. Now, what I'm first going to do is initialize my answer list. This is effectively what we're going to return at the end. It's going to be all zeros to start with, and it's going to have a length of the number of users. Just to make sure that U is capitalized. Perfect. Now, basically, this answer is going to be a list of zeros. It's going to, again, have the same length as the number of users. And answer at index I is going to track how many mentions that user I receives. Once we initialize the answer, and then I'm going to initialize online, and it's basically just going to be a Boolean list here of all initialized to true for all indices, again, also having the length of the number of users. Right? So they both have the same length, and basically the reason why all of these are set to true is because the problem statement, like we talked about before, says that initially all the users are online. So online would simply just be a Boolean of all true at first. And when a user does actually go offline, we'll then flip their entry to false accordingly once we're actually handling that process. Now, like we talked about, we're also going to get our offline queue. This is quite, did I spell Q right? I struggle to spell Q correctly. I'm going to assume that this is the way to spell it. And of course, it's going to be the minimum heap. This is the whole point of why we actually imported the heap queue. Again, we didn't really need to do that for the Leetcode editor specifically, but it is just a good process because a good practice because we are actually using the minimum heap queue operations like pop and pour. All right, this is again basically just a minimum heap to track the users that are offline, and it's going to help us let us find which offline's user return time is the earliest. So once we actually initialize offline queue, now let's get the other variable all mentions count, like we talked about in the solution as well. And that's going to be initialized to 0, where it's basically just going to count how many messages, or rather how many message events had the content all. And instead of actually incrementing every user immediately, we would simply just count those and apply them to everyone once at the end, because that would just save a lot of time and typing. Now, this is where the code really gets a lot trickier because we're going to be using a lot of different functions and built-in methods here in Python, like lambda and ord, and we'll get into that slowly, right? So like we talked about, we're still going to sort the events, right, by their timestamp, and effectively, we're going to pass in a key when sorting this. And for our key, instead of just being a random built-in key, it's actually going to be a lambda method here, right? Lambda methods are also called, anonymous methods here, basically just one-time use functions, a lot of the times just used for sorting keys like we're doing right now. Right, so it's going to take in a parameter x. Now, in this kind of method here, what we're doing is we're getting the integer of x at index 1, right? Once we get the, okay, I'm trying to make sure my syntax here isn't messed up. I don't know why we have two different, that's probably why. Let me just restart this. So, in this parameter x, we're going to have an integer of x at index 1. That looks a lot cleaner now. And once we actually get that initialized, we're then going to have the negative ord of x at index 0, index 0. And you can kind of see where this is going as we actually process the inputs here, where it's going to be a tuple, x is going to be a tuple of length 2 with a timestamp, and of course the negative ord of the first character of the event type, right? What does this line actually do? Well, effectively, we're simply just sorting the events in place, right? The key is, again, a tuple of the timestamp as the first parameter and the negative ord of the first character of the event type for the second parameter. Now we're then converting the timestamp string x at index 1 into an integer, so the sorting is actually numeric. And the negative ord at x index 0, 0 basically just ensures that when the timestamps tie, the event types that start with a character earlier in reverse order get priority. Right, that's what we talked about before. If we have that tie, this is the kind of like that second case where we'd fall into this conditional, if you will, to handle that tie, where again, basically, the event types that start with a character earlier in reverse order would get the priority. Now, in this kind of system here, basically the way it works is this orders message before offline if they do share a timestamp. And this is kind of a neat way to do it because M does have a higher negative ordering than 0, or rather than O, sorry. And one observation kind of tying back to how we can make here is that having the tiebreaker is very, very important, right, to those problems constraints. right? Because processing an offline that happens at the same timestamp as a message the wrong way will actually change the counts, which of course we don't want to do. Now, again, the reason why we're using this is for the tie because we know that M does come before 0, or O, I don't know why I keep saying 0, in reverse order. 0 and O look very similar. I don't know why I just realized that, but they do. Now, here we actually begin our iterations here. Now that we've actually created all our different lists, and now we actually begin processing through all the different events here. Now, I'm going to have 3 different iterators, if you will. So I'm going to have an event type. For my first iterator, I'm going to have a time t, and I'm going to have a message content iterator. Probably should be using such lengthy iterators, but it's fine. I'm going to be iterating through my input list events. Right, so effectively, we're simply just starting the iteration process through these sorted events, where each event would then unpack into 3 different parameters: the event type for my first parameter, the timestamp t or the timestamp string, and the message content, which would either be all here or a mention list for for offline the user ID string. Right. So once we actually get that iterator set, we're then going to get our timestamp to basically just be the integer of the current parameter or unpacked iterator t. Right, we're simply just converting the timestamp string into an integer for the actual numeric comparisons, so we can actually compare them numerically in if conditionals. Now, while, I don't know why I spelled that wrong, while the offline queue is non-null, meaning while offline queue in Python, we could say equals true, but we can just say while the offline queue, because that basically just checks while it's non-null, while it still has elements to actually pop off, and offline queue, I think there's an E that comes first, or is it a U? I don't know. I think it's a U actually. At index 0 dot return timestamp is less than or equal to the current timestamp. While that's the case, we're going to get the user and set that equal to heap queue pop off, so heap pop from the offline queue. And I just realized there is actually 2 P's in the heap pop operation. Once we actually set that equal, we're then going to get the online index at user.id and set that then equal to true. Because it now has become online, we're flipping its conditional, or rather we're just changing it back to true if it was false before. Now, how does this really work? Well, before actually handling the current event, we're simply just popping from the heap all offline entries whose return timestamp is less than or equal to the current timestamp. Now, for each popped entry, we then set online at user ID to true, and that basically just brings users back online once their 60-unit offline window has actually ended. And the reason why we're using this heap is because it's very efficient, because we're only actually examining the earliest return times, rather than any other way to process them, which is why we're actually using the minimum heap, right? So now that kind of confirms and brings off that setting it equal to. Now, what if our event type is a message? Well, that's where we get into the next part of this solution. So if the event type itself, in the current iteration here, if it's actually equal to the message type, and I think it's all caps, well, what if that's the case? Well, if the event is a message, we have to then inspect the message content to know how to actually credit the mentions. So if that's the case, and message content is equal to all, if we have an event type of message, we'll then increment our all mentions count by 1. And the reason why is because if the message is all, that means that every user should be credited once. And instead of actually adding to every answer right now in this iteration, we can simply just increment the all mentions count, and we can just add that to each user at the end. It's a very neat optimization trick. And it reduces a lot of repeated work that we'd have to do on the answer itself, which we really don't need to be doing. It really just makes this a lot less efficient, which no one really wants to have. And again, tying back to another major observation to make, counting all would lazily reduce complexity when there's too many all messages, right? That's the reason why we're doing it like this with the all mentions count, rather than just directly working with the user, or rather working with the answer. Now, once we have that, what if it's the other way? What if the message content is here? So if message content is here, well, what do we do there? Well, that basically just mentions all the users who are currently online. So we'll go through all the users that are currently online. So for user ID, in the range of the number of users, if it's online at the user ID, meaning if the current user ID has a online value of true in the online list, well then we simply increment answer at user ID by 1. Right? Basically, we'd loop over every user and increment answer at user ID only if online at user ID is actually true, meaning they're actually online. And the reason why this is very important and essentially required is because here is relative to the current online set, and so we must do it at this timestamp after actually bringing the expired offline users back online. Now, if neither of these event types are true, in the else conditional here, if message content isn't message, or here if it's a specific mentioned list and it's more formatted like U3, U0, or U12, well then we actually have to process it by going through every user ID and the message content after splitting it. So basically the way that would work in terms of syntax is int, and I'll explain this once I actually finish typing it out, from index 2 till the end for every part in message content. And we're going to split message content. Right? We're going to increment answer at this user ID by 1 once again. Now, how does this really work here? Well, otherwise, the message list essentially explicitly mentions formatted content like U0, U3, U9, U4, things like that, right? That's how we actually fall into this else conditional here. And the way we'd handle that is we'd split the string on spaces, and we'd essentially just strip the U prefix by taking part from index 2 till the end, assuming that the form is U and then whatever ID. And then we'd actually convert it to an integer, and for each mentioned user ID, we'd increment answer at that user ID. Again, tying back to another major observation here, the part from index 2 till the end, slice is very efficient because the pattern is exactly U followed by whatever digits. And so we're essentially just stripping away that prefix U for the current ID. And that just makes it a lot easier to deal with using the split method, not split, but the index splitting method here in Python, where we're essentially just passing in the parameters in the index itself with the colon here kind of telling us the range of indices from 2 till the end of the actual string, right? Now, of course, it's very important to actually test this according to the problem's constraints and what the problem actually says. In this case, I believe we are guaranteed that the way that is U and then something, and so that's why I did that, right? So let's go ahead and get back to the solution here. So that's how now we actually handled all the different possible message types that we could have. Now, what if we're actually offline? We've handled all online, but what if the event type itself is quite literally just offline? Well, that would have a completely different system as well, or setup as well. And so the way that would work is, notice how we were in this kind of outer layer of the if conditional. That's if the event type was message. Only then do we actually go into all of this. If the event type isn't even message at all, meaning if it's actually offline, well then we'd exit that, and then we have an elif in the outer layer. So if the message content, or rather the event type, is equal to offline, I don't need a period there. Make sure it's all caps. If that's the case, we then set the user ID to then be the integer of message content. I think I spelled that right. Yes, I did spell that right. Perfect. Once we get that user ID and get the integer of that, we then set that back equal to false because that user at that user ID is now false. And so we're going to set online at user ID. Okay, I do not need the caps here. And set it equal to false. Once we do that, we're then going to push it onto the heap queue. So heap queue.heap push. There are 2 P's in this as well. The first parameter is, of course, the offline queue because that's what we're actually pushing onto, and the second parameter would be offline user at the length of at the tuple of length 2 with a timestamp plus 60 when they come back online, and their user ID for this user that just turned offline. Then basically, if the event is offline, and this elif statement here, well then the message content is the user string ID, like 3, 5, 7, whatever. We then parse it to an integer user ID. We'd mark online at the user ID to be false because they're now offline, and then we then push the offline user object with the return stamp equal to timestamp plus 60 into the heap. And that basically just schedules this user at this specific user ID to return 60 units later to come back online. And finally, to kind of sum up this solution here, we're then going to finally iterate through all the different number of users. So for user ID in the range of the actual number of users that we have, we're we're going to increment or update answer at user ID, like we talked about before, the clever way to do it, by all mentions count. This is the really neat way to do it. We don't have to process and work with answer directly every single time we want to update it in the different iterations. We can simply just use this all mentions count and increment that for all the different user IDs accordingly. And finally, as you may have expected, we simply just return the answer, the final answer at the end. Now, this should also be undented. And that really is it for this solution. Unless I made any syntax errors here, this should be accepted and this should be a valid solution. So let's go ahead and verify that. Okay, yeah. So like simple syntax errors here are what are very annoying. Looks like I forgot to close, or no, I forgot to add a parenthesis. Why? Why did I forget to add a parenthesis? Well, let's go ahead and check that out. Lambda x. Yeah, that seems about right. Okay, yeah, I don't know why that worked. Okay, now let's go ahead and retry this, see if it works, unless I made another syntax issue here. Let's go ahead and see that. Data class. Let's go ahead and see what else I did wrong. Yeah, so it's actually data classes. I was kind of confirming which one it was. Data classes. It's not data class. Sorry about that. Yeah, simple typing errors here are very annoying. Let's go ahead and see. Yeah, there should be capital. I don't know why I forgot to capitalize that. And you guys can just go ahead and fast forward through this part of the video. This is just me debugging my very faulty written code here. Like this should be capital. I don't know how I forgot that. Like simple capitalizations I miss. Let's see what else. Yeah, again, it's number of, right? Number of users, yeah. Let's try that again. Okay, now let's see this. It's gonna be heap q to heap push. Let's go ahead and see. Yeah, this should be timestamp. I don't know how I missed that again. Somehow I did. Really weird. Now let's go ahead and test this. And as you guys can see, it works. It is the most efficient solution possible. Although I did have some weird typing errors, this really is just about as efficient as you can get it to be. So overall, how does this code really work once again? Or effectively, first just sorting the events by the time and making sure that the message events at the same timestamp are actually processed before the offline events. And then we're actually maintaining who is currently online, and we're using a minimum heap to automatically bring the users back online when their 60-unit offline time actually expires. And for the all messages, we actually increment a shared counter and apply it at the end. It was a very neat trick. And for the here, we simply just increment the currently online users immediately. And for explicit user lists, we simply just parse through each U and then the ID and increment those users specifically. And after we actually process every single event, we then add the total all count to each user and return the result. And basically using a heap would make sure that we only process the offline return events when we actually need them. And that basically just keeps the iteration and the overall solution a lot more efficient, right? Which is why we have a very efficient runtime as well, right? So getting into the complexities of this solution. So for the runtime complexity, it's going to be an overall big O of n log n, where n is simply the number of events. The reason why is because, well, sorting really kind of dominates, like we talked about before, where sorting the events in place would take big O of n log n. And the memory or space complexity is really a lot more straightforward. It's going to be a big O of n plus u, where u is the number of users. The reason why is because we're storing the answer and the online arrays in space of big O of u, and the offline queue heap can hold up to big O of n entries in the worst case, and sorting would also use big O of n auxiliary memory, and so the total memory complexity would be big O of n plus the number of users u. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.